So good evening. I'm Sushma. So let us start today's session with the introduction to solar photovoltaics. So let us see what are included, what is the outline of this session. So today we will cover the topics like what are the types of solar energy and how we are utilizing solar energy, and then we will see the advantage of solar photovoltaics, and then we will come into working of a solar cell. So we will understand the basic working of a solar cell, how it is generating electricity we will understand, and then what are the characteristics of a solar cell. So uh, as solar cell is just like a semiconductor device, what will be the characteristics of the solar cell? Like what is the IV curve, and what are the parameters? Those we will see and understand in characteristics. And then what are the effects of radiation and temperature? So in how the performance of solar cell, in this we will understand how the performance of solar cell is affected by the weather parameters and location or installation parameters. These things we will understand, and shading, by shading what will be the effects. So these things we will understand in this effects of uh, radiation and temperature. So let us start the session. So now when we see solar PV systems, so solar radiation can be utilized in two ways. Like either we can use heat energy, or we can use light energy from solar radiation. Using heat energy, the systems developed, we call them as solar thermal systems, and using light, we call solar PV or solar photovoltaic systems. So let us understand what is thermal systems. So just with some few systems we will understand. So for solar thermal systems, what happens is mostly the heat is absorbed, and then there will be a working fluid. Using that, we generate that heat, we utilize that heat or steam to run a turbine, and then we couple the turbine with a generator, and then we get electricity. So this thing happens, but the first thing we are looking in solar thermal systems is a flat plate collector. So this ones we regularly see it upon the roofs for domestic water heating purposes. This is used. They just have very simple components. They absorb the heat, and there are pipes here. They absorb the heat, and they absorb the water is heated, and then water is stored in the storage tank. So this is very much used these days. We can see upon roofs, domestic purposes only. Water gets heated up, and and it is supplied for domestic purposes. And then it is parabolic trough collectors. So here there are these parabolic troughs are usually they are used to generate electricity. So a parabola shaped mirrors or reflectors, we call them reflectors or mirrors. So they are arranged in the shape of a parabola. So at the focal point, you can see a pipe is running at the focal point, and there is a working fluid inside the focal point, inside the pipe. So the sunlight is using the reflectors. The sunlight is reflected onto this pipe, and the heat is absorbed by the working fluid, and then this uh, uh, fluid gets heated up and forms a steam, and this steam is used to run a steam turbine, which in turn runs the generator and gives out electricity. So this is parabolic trough collectors, and they actually track the sun because sun moves from east to west throughout the day. They track the sun and generate steam. And then is the parabolic dish collector. So in parabolic dish, the reflectors are arranged in such a way to form a dish, and at the focal point, the radiation is reflected onto the focal point, so that the same way the working fluid is get heated up, and then this fluid or steam is utilized to power a turbine and then generate electricity. So next is the linear Fresnel systems. This system usually they use Fresnel lens here. So these lens they actually track the sun, and for linear Fresnel system, what they do is many like lens, you can see here many reflectors are arranged, and all these reflectors have only one pipe like with carrying the working fluid. So they track the sun, and for all these reflectors only one pipe is arranged. They track the sun and they focus the reflected radiation onto this pipe so that the working fluid gets heated up. So this fluid is again used to run a turbine and then generate electricity. So next is the central tower system. So in this central tower system, there is a lot many flat heliostats or mirrors, you call it. They reflect this radiation. They are arranged on the ground and they reflect the radiation. The total radiation reflected by all these heliostats, they are arranged in such a way that the radiation is reflected onto a central tower, where at the top of the tower, where a working fluid is kept, and it gets heated up, and this fluid is, or steam we call it, steam is used to run the turbine and then generate electricity. So there are few disadvantages with this central tower and these systems, because like whenever there is a birds flying in this area, maybe they get burnt because of the lot much of heavy heat generated, and most of the radiation gets reflected at one point. So if any insects or flies or birds, they are flying there, they get burnt. So this is about different types of thermal systems. And now let us understand what is photovoltaics. So photovoltaics is direct method of converting sunlight into electricity using a device called solar cell. So this is called a solar cell here. So here we can see here, this is a solar cell, and in solar cells we use the light from the solar radiation, and here whenever the sun shines, this solar cell generates electricity directly, and this will when we close the circuit we get the electricity. So let us understand what is the working of the solar cell. So when you see a solar cell, it is just a arrangement of silicon layer, that is P and N, like P type silicon and N type silicon. They are just PN junction. They form a junction, PN junction, and PN junction is just arranged like this. It is just like a diode. So this is like any other semiconductor device, it works. So here we understand it is just a PN junction here. So when the sun shines, what happens is when the sunlight is absorbed, like sunlight has photons, when these photons get absorbed, their electron holes are formed inside the electron holes are formed in the solar cell, and these electron holes, they get separated because of the inbuilt electric field. Because of the inbuilt electric field between the PN junction, the electrons and holes get separated, and whenever there is a potential difference or separation of charge carriers, there will be a flow of current. There will be a voltage developed, and when there is a voltage developed, the current will flow. So if we close the circuit, the current will flow. So this is how current can be delivered from a solar cell. And next is here we will understand how this solar cell material, like how this material solar cell is prepared. So if you see, mostly we use semiconductors in solar applications. So this is because solar cell applications, like the solar radiation, when we see the solar radiation spectrum, this the wavelength is very much matching with the bandwidth of semiconductor materials. So mostly silicon semiconductor material is used mostly. Majority of the majority of solar applications we use silicon solar cells only. So here mostly silicon, and this silicon is second most abundantly available material in Earth's crust after oxygen. So silicon usually it is we find it in sand, in the form of sand. We call it quartz in in the form of SiO2. So lot of manufacturing happens, like very high energies are required to purify this SiO2 and get good semiconductor grade, very good purity of silicon. So now we get them, we after manufacturing this semiconductor grade silicon, these ingots are formed. These are called silicon ingots. So these silicon ingots, they are uh, they are again cut into wafers. That is, we call it as wafer dicing. They cut into wafers and then they make as solar cells. Again, these small sleeping lines are called fingers, and these vertical lines are called bus bars. These conductors are inscribed on the solar cell to collect the generated electricity and deliver it outside. So these are called bus bars and fingers. And then we encapsulate these solar cells. We connect all these solar cell in series, and then we give it to the, we laminate them. Like all the solar cells are connected in series. So many, all about 60 or 72 cells are connected in series. And then they are, when they are connected, like first we have a back sheet, and then we have a, EVA sheet, that is a encapsulant, and then we place the modules, and then again EVA, upon that modules we keep the EVA sheet, and then a glass cover, and then they are framed. So this is how solar panels are manufactured. So usually we get in previously we used to get this solar cells from microelectronics industries, but nowadays solar has very much solar applications has increased. So the industry, we have solar cell manufacturing in India also. Previously we don't have, we used to import solar cells and laminate them here in India and make solar panels. But now solar cells also manufacturing in India also. And these modules, we have many types like polysilicon, monosilicon, and amorphous silicon. So many types are there. And we will see the advantages of solar PV. So it is a very vast fuel source. Like solar energy is available anywhere, and it is very much free, and no emission and no combustion of any fuel, or no radioactive material, high temperatures, and no high temperatures and pressures or disposals. So no moving parts. So there are no moving parts here. Low operating cost, definitely. Just we have to clean the panels regularly. And long life, like there is no particular figure that we can mention. So this is the lifetime of a PV modules. So if the system is very well maintained, and we can say it will work for more than 30 years, like that. And so there is high reliability, and the quick installation and modularity and integration, so can be installed at a point of use. So, and output during peak demand. So high public acceptance and excellent safety record. And then here is the solar cell equivalent circuit. So this is the equivalent circuit of solar cell. So here, this current source, it will denote the light generated current. IPV is the light generated current. And here, this is the saturation current, ID, and RSH, reverse current. And RSH is the shunt or leakage resistance, and RS is the series resistance that is offered when during the flow of current. So usually we manufacture, these are given, RS and RSH are given by the manufacturer only. And ID also, reverse current also given by manufacturer. And here we have the IV curve of solar cell. So let us see if you have a solar PV module, we can just get the IV curve. If we have a rheostat with us, we can just do it at a lab also. Just connect it to a rheostat. Keep the voltage as 0. That is open circuit, under open circuit condition. So we will see here V is that VOC, that is open circuit voltage. The voltage across the terminals, the plus and minus terminals of the PV module is given as VOC, that is current is 0. And then as we decrease the resistance, so I increases, sorry, VOC, I mean infinite resistance is very large. And as current I increases and as resistance decreases, current will increase and voltage decreases. So as the resistance becomes 0, it is short circuited and the current is maximum, that is ISC, that is current at short circuit condition. So this is the IV curve. So if we see an ideal solar panel or solar cell, the ideal curve should be a square, but due to series and shunt resistances and other deformities, the characteristic IV curve is not completely a square shape, not completely in square shape. And the module parameters. So if you take a module, solar PV module, what are the parameters we get from the manufacturer, like ISC, VOC, what is the maximum power generated from the module, and what is the at maximum power, what are the voltage and currents. So these things the manufacturer mention. So these are the module parameters, VOC, ISC. Now we will see the power curve, that is V into I, because this is this solar panel will generate only DC power. So it is just V into I gives the power. So just plot a power curve with the x-axis voltage and y-axis as power. You will get this curve, and P max here at a maximum power. So what are the voltages and current? So VMP and IMP. This is the maximum power point. And these are the voltages and currents at maximum power point. So, and now we will see what is the fill factor. So fill factor means it is the area, that is VOC into ISC, that is area 1. And the area 2, it is VMP into IMP, that is nothing but maximum power point, that is PM, P max. So now fill factor is the area, that is area 2 upon area 1. It will give as P max can be given as VOC into ISC into fill factor. So this fill factor will indicate the quality of the solar cell. Usually it is maintained fill factor of 75%, like that is, we can say as good solar cell or module. So now we will understand what are standard test conditions. So whenever you see a solar PV module, so at the back of the module, we can see the nameplate details. So at the nameplate details, the manufacturer will give you the VOC, ISC, VMP, IMP, and P max. These things the manufacturer will prescribe. So when they have prescribed these, how they are giving, because the radiation on the solar cell is not always same. It differs depending on the location and depending on the weather. As throughout the day also it is differing, it is not the same. So how they are giving, so what they will do is the manufacturer will do a test. Whenever after manufacturing the solar panel, they do a test called flash test under standard test conditions. So what are the standard test conditions means? At irradiation of 1000 watt per meter square, so they arrange a flashlight, xenon arc light with a irradiation of 1000 watt per meter square, and the cell temperature they maintain it at 25 degrees Celsius, and air mass 1.5. We will see in the next slide what is air mass. And under these conditions, they test the performance of the solar PV module, and they give the maximum power given by the PV module, and what are the VOC, ISC, VMP, IMP, all these things they look at the PV module's performance under these standard test conditions and mention it as a nameplate details at the back of the PV module. So now we will see what is air mass. So air mass, it is the path length that light takes through the atmosphere compared to the shortest possible length. So if you understand the solar radiation, so outside the Earth atmosphere, all the radiation, all the sun's radiation is parallel. The radiations are parallel. So, and parallel and constant. And once they enter the Earth atmosphere, because of the clouds and because of other gases and other things, they get scattered or they get reflected. So they are not parallel. So whenever the sun is directly overhead, the length of the solar radiation is minimum. So during noon time, you can say the length of the solar radiation is minimum. So noon time. Morning and evening time, the path length is maximum. So as the path length increases, the more the path length increases, the more the scattering of the radiation happens and the intensity of the radiation decreases. So this air mass, it quantifies the reduction in power as it passes through the atmosphere and absorbed by dust and air. So it is given as this value, the path length, that is y and upon x. So this is cos theta. So usually we take it for standard test condition, we take it as 1.5. That is morning time or evening time. But at noon time, air mass, we can say noon time it is 1. And outside atmosphere, it is 0. And now let us understand, after knowing fill factor and standard test conditions, now let us understand how the efficiency of the solar cell is calculated. So cell area, here we have a solar cell and the cell area is 156 mm by 156 mm. And I have the incident energy. Now we know the area of the solar cell. We can calculate the incident, what is the solar radiation that is incident upon the solar cell. So we will see here 1000 watt per meter square. So this 1000 watt per meter square, this is just a standard test condition. But originally, when you install this solar PV module outside, so it will not, we can't say 1000 is maintained throughout the day. So it is less than 1000, or sometimes during peak hours it could be more than 1000. So exactly 1000 is not maintained throughout the day. So for understanding, for calculating efficiency, here we have given 1000 watt per meter square into 156 into 156 meter square. So here we have 24.336 watts incident energy, that is input energy. So efficiency is always output by input. So now we have VMP, according to nameplate details of the solar cell, I have VMP as 0.5 volts, IMP as 7 amps. So P max is 3.5 watts. Cell efficiency is 3.5 upon 24.336, that is 14% efficient, 14.38% efficiency. So this module efficiency is 14.38. So this is how we calculate the efficiency of solar cell. Now we will understand how the cells are connected in series. So if we have to connect the cell, if your requirement is in such a way that you want more voltage, so we will connect the cells in series so that the voltage get added up and the current remains the same. So to whenever we want to manufacture solar panels, all the cells are connected in series. So cells connected in parallel. So if we want more current, if our requirement is in such a way that we want more current, so we can add up, connect the cells in parallel, or we can connect the modules in parallel. So when you connect the modules in parallel, you have to take care that all the cells have same voltage, maintain same voltage, and the currents get added up. So this way you can connect them in parallel. And just for understanding, we will see we have a solar cell here and the voltage is 0.5 volts and the current is 7 amps. and power is 3.5 watts. So what is the VMP and IMP for this half cut, the half of this cell, the half of the above cell? So definitely it is voltage will remain same, that is 0.5 volts, because voltage is a material property. Voltage will remain same. IMP current, the current will change because as the area is less, the absorbed solar radiation will be less. When the input is less, definitely current output will be less. So IMP is halved, that is 3.5 amps, and the Pmax will be 1.75, that is 3.5 into 0.5 volt, that is 1.75 watts. So always please understand that voltage will, in solar cells, voltage is a material property and current depends on the radiation, solar radiation. And now let us understand when these two cells are connected in series. So what happens is, when in series connections, current will remain same and voltages will add up, that is 0.5 plus 0.5, that is 1 volt. Pmax will be 7 watts. And now half cut solar cells, these four such cells are connected in series. So then it will be 4 into 0.5, that is 2 volts, into IMP will be halved, that is 3.5 amps, that is Pmax will be 7 watts. Now we will understand what is the effect of varying radiation. So if you observe the sun's path throughout the day, so morning time when it starts rising from the east, the radiation will be less. So around 200 watts per meter square we get. So at that time, this will be the IV curve. So as the radiation increases, the IV curve also, you can see the IV curve, you can see the IV curve here. So this is the, we call it as VMP range. We always want the PV module output, give the output at this maximum power point to operate at this point. So this range is called VMP range. This range is called VMP range. The power output increases as the radiation increases. The voltage decreases, but this is very much less significant compared to the increase in current. And now we will see the effect of varying temperature. So usually the temperatures are not same throughout the year. They differ in summers in Indian climate conditions. In summers the temperature is very high. So here we need to understand that the module operating temperature of the module is different to the ambient temperature. So if the ambient temperature in summer is around 42 degrees Celsius, the operating temperature of module will be around 20 to 25 degrees more than the ambient temperature. That is around 60 to 62 degrees Celsius of operating temperature will be maintained. So as the temperature increases, the voltage will decrease and the current will increase. But if you see the curves, you can understand that the increase in current is very much less significant compared to decrease in voltage. So as the temperature increases, the voltage decrease. So this is how the effect of temperature we will understand here. And now effect of shading on PV module. So whenever we are going to install PV systems, so we will first do a site survey. So we will understand what are the surrounding conditions and what is the, if we are installing on a roof, what is the, how is the roof, where is it located, like latitude, longitude of the location, and how the building is oriented. So what is the orientation, latitude, longitude, and what is the orientation, like the azimuth angle, we call it azimuth angle of that building, and any other nearby, any other obstructions like trees or other high-rise buildings nearby the roof. So all things, and what is the dimensions of the roof and how much active area we are getting to install solar PV, and what is the dimension of all the parapet wall, what are the shadows we can expect, throughout the year. So all these things we will check before installing the rooftop, that we call it as site survey. So whenever we install a PV system, we need to take care that there are no shades falling on the system. We ensure that maximum solar radiation is falling on the system without any obstructions. So also we need to take care that when we arrange the solar PV modules in rows, we need to take care that they are distanced properly, like the mutual shadings, like one module is casting shadow on the next module. So that thing we need to maintain a pitch distance between these rows. So all these things we need to take care. So suppose if there are any shadings, like if there is any shading on the PV module, so what they do is, for a PV module, they install these bypass diodes. So these bypass diodes, usually they are connected across the solar cell in reverse direction. So whenever there is a shade, what happens is, see here you have a solar cell, the current is flowing, like it is flowing like this. So whenever there is a shade here, what happens is, this side it will not work. Whenever there is a shade here, what happens, all the current will flow through this, and this will become a load, because this is a shaded area. This will become load, and all the current is dissipated in this area. And here what happens is, there may be some breakage of glass, because all the current is dissipated here. There may be some breakage of glass, and some hotspot creations can happen. So to avoid these, because of shadings, to avoid these conditions, what we do is, they connect bypass diodes. What this bypass diode will do is, so whenever there is a shade, this bypass diode will activate, and it will bypass the current coming from other cells. Like from here it will come, and it will get bypassed from here. It doesn't go into the shaded area. So this is the requirement of bypass diodes. So suppose there is much shadow, the performance will be 0. Now we will understand the effect of the module tilt. So whenever we are going to install the PV module, as a rule of thumb, usually it is installed at a tilt of equal to the latitude of that location. So usually we do the fixed tilt for rooftop systems. We maintain a fixed tilt system only, and oriented towards south, because see, whenever we install the solar PV modules, if they should be kept in such a way that the radiation coming from sun should intersect the module at 90 degrees, so that the modules will absorb most of the radiation. If it is not perpendicular, most of it get reflected. So to maintain it, we follow some tilt rules, that usually we make it equal to latitude. And for Indian condition, because we are on the northern hemisphere of Earth, so we see throughout the year, we see the sun towards the south. So mostly throughout the year, we keep the modules oriented towards south, and tilt equal to the latitude of the location. So this is about effect of module